Swayam Prabha. Digital India. Educated India.
Let us introduce this notion of system compensation. So, negative feedback system often tries to maintain the goal in presence of some other exogenous factor, either a constant inflow or a constant outflow rate over which the feedback system exerts no control. So, in the presence of such an external or exogenous variable, how does the system behave? That is what we will try to understand today. What effect will this constant exogenous rate have? So, negative feedback systems will compensate for the additional inflow or outflow by attaining an equilibrium which will be different from the desired one. So, though we will have a goal, the system, because of the constant exogenous variable, will actually come to an equilibrium which will be different from the goal, as we will see in the using the example. So, before we go into the analytical version of it, let us take our laptops and expand the labor model that we did yesterday in the face of a constant exogenous outflow. So, let us look at what we want to do in this model. Consider same labor example. Suppose, so in the labor example there was a desired labor that a company desired, and we had the current level, and the gap was adjusted based on some adjustment time. I think the base case assumed 6 months of adjustment time. So, we had built that. So, in that consider labor example, suppose people leave the company at some arbitrary constant rate over which you have no control. People may leave the company at any point they choose. Now, we want to update the model to reflect this scenario, and what effect does this constant exogenous rate have on the system? We can start with parameter desired labor 100, initial labor 100, and the leaving rate as step. We will come to that what it means. So, let us go to Vensim and try to model this. The first one is this one. Suppose people leave the company at some arbitrary constant rate, we need to update the model to reflect this scenario. So, people are leaving, that has to be modeled. So, let us go to Vensim. So, this is the model we used yesterday. Right. Okay, I am just going to save as 2, a new version. So, let us, before we change the model, so let us just quickly click equations button f of x, click that, and just check if adjustment time is 6 months. Net hiring rate is labor gap divided by adjustment time, units is person per month. Labor gap is desired labor minus labor, units is person. Desired labor is 100, desired labor 100%. Now, let us take labor, that is a stock. I just opened the stock labor. The initial value it will say 0. So, let us just change that to 100. So, now the goal as well as actual stock is 100. So, we do not expect any new people joining the company. Now, click rate, we need to model people leaving the company. So, let us click rate, click inside the labor. So, just include a variable called leaving rate. So, there is, since it is exogenous, we do not need to show anything coming into this, it is already given us an exogenous. Let us go to the equations. As soon as you click equations, both these things will become kind of on the black background. So, let us click labor first, and you will see that integration equation has changed. Net hiring rate minus leaving rate has automatically did that. So, which is what we want. We want the stock to change by hiring rate minus leaving rate. So, all we have to do is OK, we are done, nothing to change there. Come to leaving rate, let us just put a value 0. and what should be units for this? Persons per month. It is a rate, this shall always be per time unit. We use the same time unit as the inputs. Okay. So, initial value of labor is 100, desired labor is also 100. So, then we can expect net hiring rate should be 0 and leaving rate also is 0. So, when we actually simulate the model, the labor does not change, it is always at 100, leaving rate is 0, net hiring rate is 0. This is what we mean by dynamic equilibrium. So, model starting in dynamic equilibrium, nothing is changed. Now, so we just included this one extra variable within the model. Now, let us go to our model. Say that here it says leaving rate is step of 4,5 people per month or person per month, I guess. Find out what step command does. Let us do that. Before I change the equation, see there will be many such commands. It is a pretty decent help. So, you just click help, click Vensim manual. It gets installed by default. You do not need internet for it. It will be in your local drive. So, you should open up a screen like this. Search, step, submit, you show various things. In mine it comes as option 5, so click step. The step command is a step function. So, it takes a value of height at the step time. So, until then it is 0. So, if the current time is greater than the step time, then it takes the value of height, else it continues to remain 0. So, that is what the step function does. So, there are various such functions that is available, like in other courses, most of you are either in the 4th year of undergrad or already master students. You must have studied in other courses on how to give the various inputs in the systems. So, we can have various types here, pulse inputs or a ramp input or a step functions and stuff. So, there are specific functions for each. So, this is just a simple step function. So, we want a step function of height comma time. So, pretty much what we want to model it as this input. So, this is your height and this is the time. So, value is 0 until then, before the time, and after that you take the value of height. So, in our example, suppose step is say 4,5, that means a time, okay, you can have the access 1, 2, 3, 4, 5, 6. So, step of 4,5 means at time 5, I am going to start getting a step input of height 4. So, this is 4 units. Okay. It is going to go on. It can take a positive value or a negative value the height. You can put a -4 also, it will come a pulse in the downward direction. So, you can use multiple step functions to construct whatever functions you want. There are other functions like step called ramp, pulse train, etc., which you can use to model variety of inputs within the system as required. Now, let us go to the leaving rate, and in the equation we need to type step. So, list of all the functions that is available is that Vensim supports is listed here. You can see a drop down called as function and common. So, these are the common functions that is listed here, but if you want all the functions you just select all, then every single function that Vensim supports is put here. So, you can look for step. So, once you click step, the basic key also comes there. So, step of height comma start time. S time. So, we can pretty much guess it. So, height is what we want is 4 and start time we want is 5. Okay. That is it. I just model a step function into the system. Now, let us save it and let us run the model and see what happens. Remember, desired labor is 100, current labor is 100. As soon as people leave, let us see what happens. Let us just click play, click run, let us then touch, click labor, click here causes strip, so that I can get all the graphs at one shot. Got it? Okay, so let us see. The leaving rate became a step function. Because of time resolution, you can get time step is 1. So, after that you get a increase in the next time unit. It looks like a ramp, but it is actually step function. To reduce the time unit, you can make a more clear step function. So, this is a leaving rate. So, as soon as that happened, the same goal seeking behavior is observed, where so to compensate for people leaving, that is 4 people are leaving. So, for system to reach again equilibrium, system will reach equilibrium when inflow is equal to your outflow, right? It will reach steady state again, inflow is outflow. So, system is going to keep hiring people until the net hiring rate is equal to 4, when it balances at the net leaving rate, right. So, that means how many people I am going to hire, and that will have a nice goal seeking approach that we see here. Now, let us see what happens to our actual labor. You can see that the labor does not remain at the desired level of 100, instead it now finds a new equilibrium at a point about 70, near 75, maybe 78 I guess. This is where it is attaining its new equilibrium, which is right here, which is different from the desired goal that we achieved. So, in presence of a constant exogenous variable, for example, this outflow, system will come to a equilibrium, but it is different than what the desired state will be. So, that is how system is going to behave. Because system will have equilibrium at that point, net hiring will be equal to this. So, system when it reaches steady state, hiring will equal your people who are leaving. So, system will reach steady state only at that point. So, at that point system becomes balanced. Correct, but you are not considering any extra information in the system, right. Every time only you look at the current labor, and based on that you are making a decision to hire. You don't account for this information in making a decision at all within the model, right. So, you looked at every time you look at the labor and say, okay, 4 people are short, so I am going to hire some 4 people, and I keep doing that, then I find that I am achieving a equilibrium which is lower than that. I can show you analytically in a minute. So, let us go back to the graph. Here the labor gap is at every time only looking at the desired labor and the current level of labor, and taking their difference only, and based on adjustment time trying to do the hires, okay. And system will already reach equilibrium when as soon as inflows equal to your outflows, system reaches equilibrium. So, net hiring keeps increasing until it reaches 4, when it becomes equal to your net leaving rate. So, I am not taking the leaving rate information in my labor gap. So, system will achieve a different equilibrium than your desired labor. though you decide is 100 based on the system, you will actually achieve equilibrium at a much lower level because of this constant exogenous flow. So, going back to that causes strip. So, this part here until time phi, when everything is constant, there is no change. So, that phase is called as dynamic equilibrium. After that, say until time 28 or so, system is what we call as in transient phase, and after that it reaches steady state. So, most of our analysis, so just to expand on that, let me just increase the model setting. I am just going to model setting and increasing the final time to 50, simulating it again so that we can view it nicely. Yeah. Oops. I got the same. Yeah, 50. So, about say from time phi to time say approximately 25 or 30, system is in transient phase, and after 30 system is in steady state. So, most of our analysis, especially analytical computations, we end up focusing only on the steady state systems. When does it reach steady state, or what is the value of the steady state and system, and then operate during the steady state domain. But using simulation, we need to spend sufficient time in analyzing the transient phase also, saying how the transient shape is happening, because that is what is causing the dynamics in the system. Because in reality, there is hardly any system which is operating in steady state. All the systems are in transient state eternally. So, we need to focus on transient phase also. So, we have dynamic equilibrium from 0 to phi, then we have transient phase, and then we have steady state. At steady state, you can observe that the leaving rate equal to net hiring rate, or your inflow is equal to your outflow rate, then system is steady, because then stock won't change, right. Stock change will happen only if this inflows and outflows are different. If they are equal, change in stock is 0, so stock level saturates there. And the new equilibrium value we wanted to see, let us I just opened the table to see the exact value. The new equilibrium value seems to be about 76. So, instead of 100, it has saturated at 76 as the new equilibrium value. The desired labor saturated at 76. So, let us see why that happens. Okay. So, steady state value of net hiring rate became 4 persons per month, and value of labor saturated at 76 persons. So, let us look at this behavior of steady state system or simple linear systems analytically to better understand it. But I am just going to flip the direction. Suppose there is a constant inflow and I have my negative feedback loop in the outflow. So, in face of a constant inflow, system is correcting the discrepancies from the goal and the state of system to as per fraction per time f, it corrects it. So, for this system, let us try to compute it, then you can use the same analogy to do the math for the example that you just saw. Okay. So, let us assume the same system, there is one inflow and an outflow. So, outflow is a negative feedback system, inflow is a exogenous, so a constant k. So, just to write the equations, we get ds by dt is equal to rate 1 minus rate 2. Rate 1 is k, rate 2 we are going to adjust the discrepancy. So, let us call it f into discrepancy. F is the fraction per time, that is f, I am getting f from here. So, rate 2 is fraction per time into discrepancy, k minus f into s minus s star. Okay. So, this is the system that I am simulating. Okay. When two flows affect a stock, when we did graphical integration, what did we do? We took the net rate, right. So, when two flows affect a stock, we just take the net rate, and if stock does not need to change, then net rate has to be 0, right. So, at steady state, the net rate is going to be 0. So, let me write it. When two flows affect stock, we take net rate, here net rate is same as this, right. Whatever you see here, at steady state or equilibrium, net rate will be equal to 0, because I am balancing inflow is equal to your outflows. That means K minus F into S minus S star is going to balance itself out, it's going to be equal to 0. That means I want to write it in terms of S, what is the new value of stock at which I am going to balance this out. So, if I rewrite it, I can get S is equal to S star plus K by F. This is the new value in which system is going to achieve its equilibrium. So, yes, so this is the value of stock at equilibrium or steady state. This is your goal, K is your constant inflow, F is a fraction per time in which I am adjusting the discrepancy. And yesterday we saw another expression, adjustment time is equal to 1 by F. So, in that case I can rewrite my expression as S star plus K into adjustment time, same thing. So, you can try it out for the example that we did, there you might you will find that S is S star minus of exogenous. So, the new level will be less than your desired goal by that in proportion to your inflow size. So, in this particular example, so suppose initial value is 200 and S star is 100 and F is 0.2, what will be equilibrium value, that is value of stock in steady state when K equal to 5 units per time. When K is 0, what will be steady state value of stock? It will be 100, yes, it will reach S star. When K is equal to 5, 125, yeah, it will saturate at 125 itself. That is at a value higher than the goal in case of there is a constant input. So, the input is coming which you are trying to get rid of it, but it just keeps coming all the time. So, that accumulates over time, which results in not saturating at 105, but stops at 125 in proportion to the rate at which I am able to adjust the discrepancy. Because average time to adjust the discrepancy is 1 over F, which is 5, and 5 times K, which becomes 25. So, new steady state value becomes 100 plus 25, which is 125.